Good afternoon. Before starting the presentation, I want to briefly introduce myself. My name is Insoo Kim, and I have graduated Korea University and did PhD at same university under Professor Jenny Seo. I am currently working as a postdoctoral researcher at SNUCB lab with Professor Bo Hyung Han. Today, I'm honored to present my recent research on developing domain-specific application of generative models. I'll be presenting two representative works which I have submitted. EMF3D, which integrate physics-informed neural network and diffusion modeling for 3D non-photonic device, and AGDC, an over-regressive framework for generating high-precision hybrid vector representations. Both works are currently under review at top-tier computer vision and machine learning conferences, CVPR and ICRL 2026. Here, I present fundamental challenge in computational physics and engineering. Traditional numerical simulator, such as finite different frequency domain method, provides accurate predictions on physical phenomena, but are computationally prohibitive. In nanophotonics, the science of manipulating light at nanoscale, designing devices requires solving Maxwell's equation in 3D space. A single simulation can be costly, and when you need thousands of simulations for design optimization, this becomes completely intractable. Consequently, implementing deep learning framework in 2D nanophotonic devices have shown their superiority. However, simulation situation is challenging when we move from 2D to 3D. The computational complexity scales as order of answered, and most existing deep learning approaches remain restricted to simplified 2D structures. This motivated my first research question. Can we extend the deep learning based framework to full 3D electromagnetic simulation? Here, I'd like to introduce EMF3D, a deep learning framework for volumetric electromagnetic field modeling and inverse design. EMF3D consists of three key components. Initially, we generate a large-scale dataset of 30,000 3D device field pairs using the Maxwell FDFD simulator. Each device structure is represented as a volumetric a tensor, similar to 3D representation in computer vision, enabling us to leverage convolutional architectures. Moreover, we develop a physics-informed neural network that predicts 3D EM field distributions from device geometries. This four simulation model achieves 15 times speedup over conventional methods while maintaining high fidelity. Lastly, we created a DDPM model for inverse design. The model synthesizes 3D device structures that meet target optical specifications, desired transmittance, and peak wavelengths. To our knowledge, this is the first end-to-end framework that unifies both for field estimation and inverse device design in full 3D space. Now, I want to highlight two key technical innovations that make our model particularly effective. First is our Fourier feature embedding for wavelength encoding and cyclic estimation model based on physics-informed neural networks. Penn architecture leveraged the intrinsic coupling between EM fields described by Maxwell's equations. This cyclic design allows the model to iteratively refine predictions and correct errors from the initial prediction. Second is our score-guided sampling and inverse design model. Our score-guided sampling leverages differentiable force simulator to guide the sampling process of the DDIM. This architecture suggests the integrated version of forest simulation model and inverse design model within a unified deep learning framework. This slide demonstrates EMF3D's effectiveness. Our forest simulation model achieves exceptional predictive accuracy compared to conventional 2D approaches. More importantly, we achieve a remarkable 15-fold acceleration compared to traditional methods. This dramatic speed-up transformed previously intractable design space exploration into a practical endeavor. For inverse design, our model achieves up to 76.57% of success rates. When compared against genetic algorithm baselines, our model demonstrates superior performance in both accuracy and computation time. Also, the table suggests the novelty of score-guided samplings compared to naive methods. This work opens new possibilities for nanophotonic research and enables discovery of novel device architectures previously inaccessible through conventional design methodologies. Now, I'd like to shift to my second research project, autoregressive generation of high-precision hybrid vector representations. Although transformer-based autoregressive models like LLMs are dominant, these models often rely on discretization-based methods. As shown in this figure, discretization fundamentally compromises precision scalability. In semiconductor circuits, this precision loss can mean the difference between a functional and non-functional design. Consequently, in many engineering domains, semiconductor circuits, graphic layouts, SPG graphics, and ETCs, we need to work with hybrid representation to save the high precision by combining discrete elements like component types with continuous values like precise coordinates. This led to my second research question. Can we develop an autoregressive framework that jointly models discrete and continuous values while preserving their natural representations? As to my knowledge, our work AGDC is the first and only work that handles hybrid representation, autoregressive generation, and variable length sequence generations simultaneously. To handle hybrid sequential data, we introduced atomic unit representation. The atomic unit representation maps each variable as sequential data as concatenated version of discrete and continuous data. For example, document components in graphical layouts, such as titles and text, are mapped to atomic units, and layout components in semiconductor circuit layouts are also mapped to atomic units. With the presented atomic unit representation, I introduced AGDC, autoregressive generation in joint discrete and continuous spaces, a novel framework for generating variable length hybrid vector sequences. AGDC employs a unified architecture that processes discrete and continuous components in parallel. We represent data as sequence of atomic units, which is a hybrid representation. The key innovation is our hybrid prediction mechanism. At each autoregressive generation step, the model produces a latent representation. The discrete branch uses traditional categorical prediction with functions such as softmax for predicting the element types from the generated latent vectors. The continuous branch employs a small diffusion-based model to sample from continuous distributions from the latent vector without implementing discretizations. Furthermore, to handle variable length sequences appropriately, we introduced two technical components: an MLP-based end-of-sequence logic adjustment mechanism and a differentiable length regularization term. These enabled end-to-end optimization of sequence lengths during training. This approach preserved two distinct continuous and discrete nature, all within a single autoregressive framework. To regressively evaluate AGDC, we developed a countliner, a large-scale benchmark specifically designed for high-precision hybrid vector generation. FrontLinet comprises 334,000 semiconductor layout samples. Each sample maintains 15-bit effective precision, about 40,000 pixels. This data addresses a critical gap: the scarcity of benchmarks where precision errors directly impact functional performances. What makes ContLayNet particularly valuable is that precision matters here. As shown in this comparison, reducing precision from 15 to 8 bits through discretization leads to functional circuit failures. We also introduced specialized evaluation metric based on design rule checks, which is standard practices in semiconductor manufacturing. These presented metrics measure the overall functionality of the semiconductor layout. For example, the circuit linkage constraint checks whether all layers of circuits are functionally valid. These metrics quantitatively capture whether generated layout satisfies essential manufacturing constraints. Here is the result of AGDC. Our model demonstrates superior performance across three diverse domains. Firstly, on ContLayNet, AGDC outperforms both baselines, layout transformer, and DLT across all design rule check metrics. Layout transformer is conventional transformer-based over regressive generation architecture that implements discretization, and DLT is a diffusion layout transformer which implements diffusion network to avoid the discretization but generates the whole layout in one-step generation, in diffusion generation. The qualitative result showed that layout transformer generates oversized layers with excessive overlaps, as you can see here, while DLT produces many noisy elements due to the poor length control, as you can see in the right bottom side. On the other hand, AGDC produces more balanced, well-distributed layers better that better align with real sample distributions. Also, quantitatively, our AGDC outperforms both baselines in all four design rule check-based metrics. Our evaluation studies also confirm that both key components, the EOS logic adjustments and length regularization contribute meaningfully to the performance. For graphic layout generation, as you can see in the upper left side, AGDC consistently outperforms baselines. The high-precision layer transformer tends to generate collapsed samples, and DLT generates slightly noisy elements, when our model generates samples that are most similar to real samples. For text-to-SVG generation, AGDC is the first method to preserve continuous nature of control points. AGDC generates continuous vector outputs with inherent infinite precision, with quality comparable to baseline's best low precision outputs, where high precision icon shops in 9 bits or 10 bits tend to fail completely. Our evaluation study also confirmed that both key components, the EOS logic adjustments and length regularization, contribute meaningfully to performance across all domains. Let me summarize the broader impact of these two research projects. Both work share a common philosophy: developing a domain-specific AI solution that respects the fundamental nature of the underlying problems rather than forcing them into generic frameworks. EMF3D treats electromagnetic simulation as 3D as a specialized version of 3D visual learning, while AGDC preserves the hybrid discrete continuous nature of engineering vector representations. Beyond immediate applications, both projects contribute new benchmark to the research community. EMF3D provides the first large-scale 3D electromagnetic field dataset for nanophotonics device simulations. Also, ContLANET offers a rigorous benchmark for evaluating high-precision vector generation, where functional correctness is measurable. Currently, EMF3D is under review at ZVPR 2026, and AGDC with ContLANET benchmark is under review at ICRL 2026. I've also filed patent applications for the AGDC algorithm through Samsung Electronics collaborations. This is end of my presentation. Thank you for listening.